Hello, everybody. I hope I'm audible. Kindly confirm, give me a thumbs up that I'm audible and that there is no echo. Unnecessary echo should be not there, or there should be no disturbance from my fan. Yes. Okay. All right. I think few of you were trying to raise your gives me a thumbs up, and then you have raised your hand, right? All right then. Okay. Let's start with me introducing myself. My name is Diksha Karapurkar. You will be seeing me over next 1 month that we are together. We are meeting on every Tuesday and every Friday from 7 p.m. to 9 p.m. This time has been chosen such that few of us might be involved with some of the engagements that we have in the morning time. We might be finishing it in the evening, and that is one reason that brings me to keep this particular session to start at 7 p.m. We will start at 7 p.m. Occasionally, it starts sharp at 7 p.m. and lasts all the way to 9 p.m. At times, we may finish a little later, um, depending upon if we have a lot many things to interact with. However, everything is going to be very, very interesting because all of us come together for the same purpose, that is habitat mapping. I have been involved with coastal dynamics mapping and monitoring and mathematical modeling, and with regards to this, often I require to prepare habitat maps in order to find out those ecologically sensitive areas. Yet again, going to ground and bringing these data, primary data, collecting primary data was very, very difficult. So, what made me realize is that it made me realize that I can definitely rely back, turn back to these remotely sensed data and some of the secondary data that is available. Now, there are different types of sensors out there that you can use for habitat mapping, and the best ones that I realized were essentially the synthetic aperture radar, that is SAR data, and the optical sensor data, that is a multispectral data sets. Now, these are the two kinds of data sets that we are going to work out with in order to identify habitats, different types of habitats we are going to map. At times, one independently, we are going to map few habitats independently. That means we are going to only locate only those habitats. Whereas at times we will try to map several of the habitats together, right? Two or three, like that. And then we will also try to merge all these habitats together, look at which are those regions which are overlapping, those regions which are showing affinity to two different types of habitats or three different types of habitats or multiple different types of habitats, or few of those regions which are only susceptible to one kind of habitat. All right. So I believe we are already for 4 minutes in this particular class. uh, Let us start. I've made a small very brief presentation for you all. This is the starting. This is where we start. This is where we get acquainted with what exactly this particular course is about. And please um, keep this with you that it is going to be a completely hands-on session, in the sense that we will have few theory sessions. And in fact, when this particular course was designed and we started advertising it, we also made a corresponding group, that all those who are interested maybe in joining in future, or maybe generally otherwise also interested in learning habitat mapping and what is the role of remotely sensed data in mapping habitats, different types of habitats. We made a group for them, and we got them acquainted with the basic types of data, what exactly remotely sensed data is, and what are the different platforms from where we can download satellite data, to import the satellite data, to view them, what exactly these band composites are, and things like that. right? So I have made a small presentation for you all. We are starting with a presentation. We have a hands-on wherein we will download SAR data and one multispectral data. So that is the hands-on for today. It is going to be a very very simple hands-on, such that nobody feels burdened there are too many things. And mind me that the entire course is going to be a cakewalk for you. So don't be worried that I have not previously worked with QGIS, or I have not worked with satellite data or anything of that sort. We start from the very basic and we go to the very end, until when we have already gained enough confidence to be able to map habitats, and also to go beyond and learn new skills that might be beyond the scope of this particular course. But we will have enough confidence to learn them on our own, because the similar techniques we must have already covered in this particular class, right? All right, so yet again, my name is Diksha Karapurkar. We are already 7 minutes in. Let's get going. I hope I was audible all throughout and that my screen is also visible, right? Just give me a thumbs up yet again if all is good. Okay. All right. So now, all throughout that this session goes on, you are going to answer these questions to yourself, and then once the session is over and once the interaction session starts, you're going to tell me, or rather, going to tell all of us, whoever is there in this particular meeting, we are going to tell me as to what made you join this particular class and what are your expectations. If you're fully, what are those things that you feel should be included in this particular course, right? Or what are your generally basic requirements that you would want to be okay. So the name of the coursework is Habitat Mapping, using remotely sensed data. What it means by when I say remotely, it means without coming in direct contact uh, with the ground features. May it be mangroves, may it be wetlands, may it be any kind of habitat, no, may it be any kind of land is land cover type, or any kind of object that is lying on the planet, or that is dwelling itself on the planet, without coming in direct contact with this particular feature, collecting information pertaining to it. What is its chemical, its physical parameters, its physical chemical attribute. This data, when we collect it using sensors that are mounted either on a satellite or on an airborne sensor or airborne instrument, and we collect information pertaining to these features, that is when we call it remotely sensed. Okay. And it is definitely a data that we require at any point of time. If you want to say something or anything of that sort, please raise your hand. If you have raised your hand for now, you may please like undo it. Like, I see that one of us is raising our hand. Let me just check. Somebody seems to be raising their hand. Shantanu, is it? Okay, just check if you're raising your hand because you want to say something. All right. If you're not, then you may lower your hand. All right. Let's get going. So before we begin, what exactly our outcomes are going to be in this particular session? Sorry. Okay. So today we will learn what is the distinction between these synthetic aperture radar, that is radar sensors, and what is the difference, how they are different from that of optical sensors. So how the satellite data that is obtained by an optical sensor and that by a SAR, that is radar sensor, is different from one another. And when do we use each of these data set when it comes to habitat mapping, which kind of data, that is whether optical or radar, we should use in mapping a particular kind of habitat. All right, so this is the first outcome that we are going to gain at the end of this particular class. We will also discover and download some multispectral, that is Sentinel-2 data. I have also shared a video with you to download Landsat data, but if time permits, we will also look into downloading Landsat data yet again. And besides that, we will also learn how to download Sentinel-1. These two, that is Sentinel-2, Sentinel-1, as well as Landsat data, these are all free of cost. We do not have to invest any capital in terms of accessing with these data sets, and they are freely downloadable, they are freely available in the public domain. We will also be able to read and verify file formats. We will see what are the different types of file formats that are available, what exactly are the coordinate projections for our data set, because some of you might be downloading a different data set than that of me. I could be interested in a completely different area of interest, and you could be studying a different area, right? So, which coordinate system do we exactly belong to, geographic as well as projected coordinate system? That is what we will look at. We will look at what is bit depth, and for some, we will also set up a clean folder, and we will understand the naming convention such that our project becomes reproducible. There has to be a specific way in which we name our files, or which we name all the data sets that we generate or that we download to be used in a particular project. And this naming convention, how it is going to be more convenient, such that no matter how many days or months after we come back to this data, how do we identify what was the purpose of making this data, or in what order did we make them. So these are also very important, and that is why we will take up naming convention for these data sets as well. Now, before we start with this particular class, what we need to have, we need to have a software, that is QGIS, the latest long-term version, downloaded and installed in our system. If we do not have it, nothing to worry, because this particular class is recorded. So if you happen to not really be able to install QGIS before this, then you can work out on it. You can share your difficulties with us as to what were your problems that you face. We will try to solve this together. And then once your QGIS is ready to work with, then you can yet again watch this particular video and get yourself acquainted with it, right? Now, besides that, you need to have an account on USGS Earth Explorer, or Earth Data, or USGS Glovis, or yet another platform that we are specifically going to see today. There were some videos that were shared with you in order to be able to download data sets from Earth Data and USGS Explorer, as well as Bhunidhi also was there, which is an ISRO NRSC data order and dissemination portal. Besides that, there must be a video also on how to download dataset, that is Landsat dataset from USGS Glovis. So today we are essentially going to look into Copernicus data space ecosystem, which is for Sentinel-2 as well as for Sentinel-1. Okay, so this is one that we are going to look at. Now, those of you who have participated in this particular course, we will be also working with some parts of Google Earth Engine as to how to acquire data without going through downloading the bulk data sets. So that is yet again one thing that we are going to look at. Now, throughout this particular coursework, I would want you to have at least 20 GB of space available within your device, right? And make sure that you keep a backup of it, just in case if something went wrong with the system, that you have to have the data set and you can work on a different system, right? Now, I have not sent any data set to you so far, but there is a pre-class download that will be sent to you if at all any of you require. But usually we try that all our participants are able to and capable of downloading their own data set, finding out which is the data set that they require and should be able to download it. So often participants don't really require it, but in case, then we already have made some data set that you can directly download. But it will be always wise that you download your own And if you are facing any difficulty but you have to move ahead with the classes, then you will be able to download these pre-class download, that is Sentinel 1 and Sentinel 2 tile. Okay, Sentinel 1 is SAR. We will yet again look at it. Sentinel 1 is SAR data, that is, it is a microwave sensor. And then Sentinel 2 is a multispectral data, that is, it works in the visible and near infrared and thermal infrared sensor, thermal infrared range. So optical versus radar remote sensing. This is the first concept that we are going to deal with. How optical data is different from radar data, and how they help us in different kinds of in achieving different objectives with respect to habitat mapping. So this is the first thing that we are going to address. Towards your right hand side, you will be able to see this very familiar picture. It reads active sensors and passive sensors. Let's talk about these passive sensors first. What exactly these passive sensors are? They do not have a source of illumination of their own. So in this case, what do they do? What do they do? They make use of some external source of light here, which is our sun, right? So from sun, we are receiving some electromagnetic radiation, that is solar energy we are receiving. It comes at the planet, it interacts with different features that are available on the ground. That includes water bodies, that includes land, barren land, agricultural land. It could be some inland water bodies, it could be some vegetation, and different types of vegetations are possible, and so on and so forth. So this incoming solar radiation interacts with all these ground features, and then the solar radiation gets reflected back after getting modified upon interacting with these ground features. They yet again set its journey towards to these sensors which are on board some spaceborne vehicles that we call sensors, sorry, satellites, right? So that is where on the satellites there are sensors available, and these sensors will sense the information or the reflected light that is coming back after reflecting from the ground features, and it is sensed, and then it is produced in terms of these imageries that we use. Now that is about passive sensor. It doesn't have a source of illumination of its own, that is, the energy source is not on board. It has to depend upon an external source of light. That means at night, when sun is not illuminating the sky, that is when these passive sensors will be completely useless in the sense, whatever data that they capture is not going to be usable, right? Now then comes these active sensors. This is slightly expensive, not slightly, way more expensive when we compare them to passive sensors. So these active sensors have their own source of illumination. So they have a light source that always directs some energy towards a planet, where it again yet again interacts with the planetary features, and some light after being modified upon interacting with these ground features, it gets reflected back and is sensed at the sensors, where it is where the data is captured and it is produced in terms of being usable for the user. Okay, now these are the two types of sensors. Coming to these passive and active sensors, optical sensors are essentially passive sensors. Optical sensors are the ones which essentially work in the visible spectrum range and the near infrared spectrum range, and they are able to function only during the daytime. That is why they are called passive sensors. They measure the sunlight reflected from the earth in visible, near infrared, and also shortwave infrared wavelengths. It requires daylight and clear atmospheric condition to function effectively, which means if there comes any cloud cover, then what is going to happen is that no data from the planet surface will be received, because it will be shadowed, and we won't be receiving any data. But on the other hand, sorry, radar or synthetic aperture radar, that is microwave sensor, is an active sensor. It means that the sensor is mounted even with a source of its own illumination, such that the source is inbuilt in it, is intrinsic to it, and whatever energy it transmits towards the planetary features will be modified and reflected back to the sensor, where sensor will sense it. Now this sensor it actively transmits microwaves and and measures backscattered energy, how much energy is reflected back or backscattered from the feature that is under study. It operates independently of weather condition, which means that whether it is daytime or it is night time, the sensor is not bothered about it because it has its own source of illumination, right? And also that because these are microwave sensors, they have higher wavelength and lower frequency, they are also able to penetrate some clouds, right? It is also able to penetrate through the clouds. And also if there is some light rain, no, some drizzle is there, then it can penetrate through that as well, and then grasslands, may it be mangroves or anything of that sort, it can interact with it. And then what is going to happen, that light, that energy, that microwave energy will also be reflected back scattered, and where the sensor will pick it, and we will have the data in spite of having some cloud cover, which is not possible in the passive or optical sensor. There could also be some smog, so there could be also some fog, and it will still be able to penetrate because these are microwaves which are very less affected by either clouds or some mild rain or smoke or fog, right? So that is why active, that is radar sensor, is though it is slightly more expensive as compared to that of the optical or passive sensor, um, we get information day and night, right? But that is not the case when it comes to optical, or which are essentially passive sensors. Now, what each of them measures? These optical measurements, that is optical sensors, they are measuring the optical the surface reflectance within this visible spectrum and near infrared, and to some extent the shortwave infrared as well. Now, these are unitless. The surface reflectance that has to be ultimately measured after correcting the satellite data, that is the optical satellite data, for the atmospheric disturbances. They are essentially unitless, 0 being completely absorbed and 1 means completely reflected. And usually all the features will reflect somewhere in between, their surface reflectance will be somewhere in between that 0 of 1, but 0 to 1. However, because these values are going to be fraction at fraction level, correct, no? So they are often scaled to 10,000, right? Often scaled to 10,000. So if surface reflectance comes to be 0 0.9, then it will be multiplied by 10,000, right? So when we multiply 9 by 10,000, what is the value that we get? We get 9,000, isn't it? So if it was to be 1, we would have received 10,000. And in such order, such that even the fractions at the third or the fourth decimal place as well becomes more conspicuous, and we can mathematically operate on them. Now, what are the different kinds of bands that we get? Often these, not often, every time in fact, these optical sensors, what we also call multispectral data set, they will be given to you in terms of different bands. For example, Landsat 8. Right, Landsat 8 and Landsat 9, both of them have around 11 bands. So each band represents a specific bandwidth within the electromagnetic spectrum, within this VIBGYOR, that is visible spectrum, or the infrared radiation, or the shortwave infrared, or the far wave infrared, right? So so different bands will be available. You will have red, green, blue. In case of Landsat 8 and 9, you also get a deep blue, that is a coastal aerosol band. You have near infrared, you have shortwave infrared 1, shortwave infrared 2, thermal infrared bands also you have. So these are the different bands that you will see in optical measurements. The thermal bands will also measure the brightness temperature. When it comes to Landsat 8 and Landsat 9, we have band 10 and band 11, which are thermal infrared bands. So they measure what is the brightness temperature, what is the temperature of the land, or maybe of that of the ocean, right? Now, coming to the synthetic aperture radar or the microwave sensors, what do they measure? They measure the backscatter coefficient, that is sigma naught or gamma naught, in decibels. They are essentially looking at how much of radiation is getting backscattered, that is within the microwave, in two different components, that is a horizontal component and a vertical component. What exactly it is, we will talk in more detail a little later. Now it depends upon the surface roughness, how rough the surface is. For example, if you talk about a deciduous forest and you talk about a grassland, right, when you look at it from far, you will see, you will realize that the grasslands are look more smoother, whereas that of deciduous forest, they look more of bulbous or more of irregular in its surface, isn't it? Somebody's trying to join. Okay. So these synthetic aperture radar or the microwave sensors, they are essentially measuring how much of radiation is backscattered from the surface where they reacted with, and this backscattering will depend upon the surface roughness, how rough the surface is of a given feature, or what is its moisture content. Now, if the moisture content becomes higher, for example, if we only talk about soil, no, when the soil is very dry, right, when the soil is very dry and you look at it, it will be reflecting very bright. But then as you start slowly adding some moisture to it, it becomes moist, it also becomes darker, which means what, that it is able to absorb more of radiation. But if you keep adding water to the soil, then it reaches a saturation point where all the pore spaces are filled in with water, and slowly a thin film layer of water starts surfacing on this particular soil. So now what happens, once it comes to saturation point and it develops this thin film of surface water layer, what is going to happen, the reflectance is yet again going to increase, you see that. So when this soil was completely devoid of any moisture, it was completely dry, it was reflecting very brightly. If you started adding some water to it, its reflectance reduced, it became more and more darker. But at some point wherein it reached its saturation point, a thin film of water layer developed on top of it, which is able to reflect much better, because it is a smoother layer, correct, no? So the moisture also will influence the amount of backscattering that is occurring at the surface of any given feature. Besides that, also the structure will also define what is the amount of backscattering that you measure, that you as in the microwave sensor measures, right? So here the gamma naught is preferred for terrain application. I have told you that there are two backscatter coefficient, one is in the horizontal, one is in the vertical. One is the horizontal component, other is the vertical component. What exactly it is, we will try to understand it with respect to a diagram later. But among this, you have to remember that the gamma naught is rather more preferred to understand the terrain application. For if we want to understand how the terrain has changed over a period of time, for example, at once, let's say it was covered by some water because the region was flooded, so the topography will be different. But when the flood recedes, then the topography of the land is going to be different, right? So in order to understand how the topography changed with the time, or to what extent a particular kind of topography was existing, for example, if a certain region was flooded, so for a certain period of, for that particular period of time wherein it was flooded, you will see a huge area that shows smoother surface or smoother topography, right, or smoother terrain. But after some time it starts showing back again the undulatory topography. So it is also used in order to understand how the topography changes, surface topography essentially here we are talking about. Now, there are these three types of sensors that you might choose to work with. We will be essentially dealing with Sentinel-2 data and Sentinel-1 data. The problem is what you know. I have kept my like if you talk to me, then I won't be able to hear it very well, right? So if there is anybody who is trying to talk, what you can also do is you can drop me a message. So if you drop me a message, I think I should be able to read it, right? I hope that did not happen wherein you were trying to talk to me. I'm really sorry. I Yes, the PPTs will be received by you all right? Okay, so please let me know. You can drop me a message, that will be much better, because I have kept my mobile phone sound to the minimal so that it doesn't enter the microphone, all right? I hope I have been clear all this while whatever I'm talking. Are you fine, comfortable with the language that I'm using, everybody? Okay, are you following? Am I too fast, or am I fine? Like understandable, right? Am I speaking the language which is understandable? Yes, yes, all right. The thumbs up really brightens my mood up. All right, thank you so much. Okay, so there are these three types of satellite data sets that we will essentially be dealing with. That is Sentinel 2, Landsat 8 or 9, and Sentinel 1. So these are essentially four, but then Landsat 8 and 9, both of them are identical, the type of bands that they have. Only that Landsat 9 is slightly more calibrated, but then you need not know what exactly it is if you don't want to dwell in over there. So I will be essentially dealing with Sentinel 2 and Sentinel 1 data, because Sentinel 2 has a better resolution. I get some bands which are 10 meter in resolution, whereas when it comes to Landsat 8, no, or Landsat 9, they are essentially 30 meter multispectral resolution. That is why I will be dealing with Sentinel 2, but then some of you might be using Landsat 8 or 9, and that's just fine with it, okay? But you will get to know which one you really want to use. You will be able to decide which one you would want to use on your own, so don't worry about it. So let's just talk a little about these three sensors. Let's get acquainted what exactly they are. Sentinel 2, we are going to use the L2A, level 2A data sets. What it means is that we are not going to deal explicitly with the atmospheric correction in this particular module. I will definitely share a video with you in order to be able to correct the data set, that is Landsat 8 and 9, as well as you can do the same thing on Sentinel 2 if at all you end up, wanting to go all the way from the raw data. Yes, I want to see how exactly atmospheric correction is to be advocated on Sentinel 2 data. I will send a video to you. You can work it out on that. However, that is slightly beyond the scope of our course, because of which what we are doing is already there is some atmospherically corrected data sets that are available, and we are going to use them directly, and that saves a lot of time, a lot of trouble, wherein we have not brought in any radiometric data, or sorry, spectroradiometer data from the field, so that we know what is the optical thickness of the atmosphere and what are the different types of contaminants that are present in the atmosphere, because of which some disturbance can be faced within the data. So we don't, in absence of all this field data, what we do is we directly use some atmospherically corrected data itself. Okay, that saves a lot of time, and it serves the purpose. That's the best thing about it. So we are going to go for Sentinel 2 level 2 data set. Always remember that level 0 or level 1 means it is raw data. So level 2, L2, means it has been pre-processed, right? So besides that, some pre-processing that we require, that we will be doing. We cannot escape from that, but it is going to be very easy, so don't worry. In fact, the entire course is going to be very easy, right? So don't feel that you will be left behind, that there will be certain things which will be very technical. Even if you are coming from a non-technical background, be comfortable, learn what you understand. If you don't understand something, please ask, interact, and let's solve the difficulties and move ahead. All right. So when it comes to Sentinel 2 dataset, we are going to use level 2A datasets, which are already atmospherically corrected. So these are spectral reflectance data in themselves. We have resolution, some bands which come at resolution of 10. There are especially four bands that come at a resolution of 10. When I say resolution, I'm talking about the pixels. If we take a picture of our friend, or even if there's a picture of ourselves in our phone, if we keep zooming in, at some point you will realize that it is pixelating out, correct? No, it is breaking apart into small small pixels, and each pixel has one tone of color only, right? So when I say that Sentinel 2 has a resolution of 10 meter, that means 10 meter by 10 meter is the size of each pixel, and likewise there are multiple pixels within that particular data set, representing a ground area. Okay, so there are some bands which are 10 meter in resolution, some which are 20 meter resolution, some which are 60 meter in resolution. That is what we call spatial resolution, the size of the pixel. Pixel is like that small square square that has one specific tone to it, essentially gray, but then we can impart different colors to them. And it has two sides. Essentially it's a square. Okay, so it has two sides. One is 10 meter, another is 10 meter, which is 10 into 10, 100 square meter, right? 100 square meter of area is together taken as a mean reflectance and is given to you in terms of that array. Now, it has a revisit time of 5 days. That means each region will be rephotographed or recaptured, revisited after every 5 days. Okay, and you have ranges from very near infrared, and then shortwave infrared spectral range. So all the way there you have also that is red, green, blue. That is a visible spectrum bands also are there. When it comes to Landsat, we have Lancet 8 and Lancet 9. We can call them brothers. They are both twins. Not really twins, but both of them are brother satellites in the sense that both of them have the same bands of the same spectral composition and also of the radiometric composition. However, slightly different in terms of its calibration, which means both of them can be interchangeably used. Okay, Lancet 9 has been operational ever since I think 2021, I believe, somewhere in April or something like that, or December 2020. I'm not able to really um, collect what exactly it was. I think December 2020 or something like that. All right. So both of them are similar. We are yet again going to use level 2 data set. Um, this Landsat 8 and 9, they have some bands, that is band 1 to band 7 and then band 9. They have a spectral resolution of 30 meters. So that means the pixels are 30 meter by 30 meter. 30 into 30, it makes it up to 900 square meters. So a huge area, no? 900 square meter represented as one pixel, whereas when it comes to Sentinel, it is just 100 square meter represented as one pixel. So which means a Sentinel 2 is a better resolution. It has a better resolution, that's what it means. Okay, more clarity, more complexity you can perceive through Sentinel 2 dataset. However, it has been available ever since I think only 2018, I believe. Only since 2018 only you will get this data, whereas Lancet 8 has been available ever since 2013. So that particular concept also comes into picture. Then there is a panchromatic band on Lancet, which is 15 meter in resolution, and Lancet 8 and 9, both of them have a 16-day revisit cycle. But then because Lancet 8 and 9, both of them are working simultaneously, I believe it has come down to 8 days, right? So every 8 days you will have your area of interest being pictured or photographed by either Lancet or Lancet 9, Lancet 8 or Lancet 9. Then comes a Sentinel 1. This is synthetic aperture radar. That means this is a radar sensor that measures the microwave backscattered energy from the planet's surface. So it works in C band. When I say C band, it also tells you that it is a specific wavelength. You can also read a little about L band. So these synthetic aperture radar or the microwave sensors, they work in C band, L band, or multiple other bands. But Sentinel 1 works in C band, which has a wavelength of approximately 5.6 centimeter, and the pixel spacing, that is your grid, that is your spatial resolution, is 10 meter yet again. And the repeativity is 6 to 12 days revisit frequency. In Sentinel 1 we have three different sensors: Sentinel 1A, Sentinel 1B, and Sentinel 1C. Similarly, I think in Sentinel 2 also we have three series. That means there are three different satellites. They were launched at different time periods, such that there is repeativity that is ensured. Continuity that is ensured. So Sentinel 2 has Sentinel 2A, Sentinel 2B, Sentinel 2 3. Some, I believe, even Sentinel 5 data we will be using. So please keep that in mind. 5P tropomy data also we are using. Okay. Um, so I'm not really able to include everything at once in this particular PPT. Whatever is here it is something that is major chunk of it, and besides that, certain other data sets that we will be in need of in order to be able to, increase the accuracy at which we are able to map a certain given habitat. So there are some other tools that will also be coming up, and that will be notified to you time and again, so don't be worried about it. Now, then comes this is one concept that we want to study, that is a synthetic aperture radar polarization essential. Now when I say polarization essential, just have a look at these three axes. These are x, y and z axis. So here you will see these red lines that define an oscillatory pattern. This is the vertical component. So this is the direction in which you will see some backscattered images that are sorry, backscatter energy that is being received at the center sensor, so which is vibrating in the vertical section, right? So that is what we call V. Okay, in the vertical section it is vibrating. And then we have a horizontal component as well. You see this blue, so it has been defined as H. Now these are called, there are some polarization codes depending upon the transmit signal polarization, what kind of signal was transmitted and what kind of signal was received. Definitely polarized forms only we are taking into consideration. So when the polarization code is VV, it means that the transmitted signal, transmitted polarized signal from the sensor was vertical, and what returned was also vertical. Okay, and then we have VH, that means the transmitted signal which was polarized yet again was vertical, and then what returned back was horizontal. Then we have combinations of this when the transmitted signal was horizontal and whatever signal returned it was vertical, and then we have horizontal. That means whatever signal we had sent was horizontal, what we received was also horizontal. Now when it is co-polarized, that means we sent a horizontal polarized signal was transmitted towards the planet, and we received also horizontal, or that we transmitted vertical signal and we received also vertical signal, then we call it co-polarized. Now this kind of component we will look at it in more detail when we actually see the SAR one, that is Sentinel one data. But let's just understand a little about them. So when they are co-polarized, no, these are more sensitive to surface scattering. Okay, these are more sensitive to surface scattering from soil or from smooth water surfaces. So you can identify some smooth surfaces or some. Yes, Sanjay, you want to say something?
Hi, I put my question in the chat. I just wanted to check the type of sensors these are.
Yes. Yes. Please repeat yourself.
I was wondering when it comes to Landsat and Sentinel-1, Sentinel-2, are all these passive or active, or these are mixed?
Okay. So the Sentinel-1 satellite, that is a synthetic aperture radar, is an active sensor. But when we talk about Landsat 8 or Landsat 9, and we talk about Sentinel-2, then we are talking about these are being passive sensors. That is, they do not have their own source of illumination. They have to depend upon daylight.
Sure, thanks. Yeah.
Eh, could I answer you?
Yes, thank you so much. Thank you.
All right. Okay. All right. So these co-polarized signals that we transmit as well as receive at the synthetic aperture radar, that is Sentinel one exactly we are talking about, they help us in understanding how a surface scatters back. And essentially soil and smooth water surfaces, wherever water is stagnant, these kind of features are very well identified using these kind of copolarized signals. It indicates structural properties of the targets, how the surface of a given feature is. Then comes a cross polarized, wherein you have a horizontal polarized signal that is sent, and what you receive is essentially a vertical one. um, this is to do with the dominance, whether the vertical component is more or the horizontal component is more. So we have HV, that is horizontal and vertical and horizontal polarized signal transmitted and then reflected respectively in that particular position. So these are more sensitive to volume scattering within vegetation canopies. So wherever you have high values of these cross polarized sensors, they suggest that there is a complex. Am I audible? Am I audible? No, I think you're not able to hear me. Just give me a second. I think my PC got disconnected. Yes, yes. Please confirm if I'm audible.
Please confirm if I'm audible.
Right? When did I lose you?
Right?
I
When
think I
did I
lost you
lose
when we
you?
were
I
talking
think I
about
lost
the
you when we
cross
were talking
polarized,
about
right?
the cross
I must have
polarized,
lost
right?
you when we were
I
talking
must
about
have
cross
lost you when we were
polarized.
talking about
So
cross
when
polarized.
the
So when
transmitted and the
the
received signal
transmitted and the
is
received
cross
signal
polarized in the
is
sense
cross
that we
polarized
send
in
a
the sense
horizontal
that we
signal
sent a
and what we
horizontal
received
signal
was
and what we
essentially
received
vertical,
was
or that
essentially
vertical was
vertical,
sent
or
in
that vertical
horizontal
was sent in
component.
horizontal component.
There is an echo.
Um, there is an echo.
Oh yes, all good now. Should be good. Yes. Okay. So when we are talking about cross polarized, wherein we sent a horizontal signal, we received a vertical one, and we sent a vertical signal and we received received a horizontal signal. Sorry, that is when it talks about it is more sensitive to volume scattering within a vegetation canopy. For example, if you talk about if you look at a deciduous forest, wherein the terrain is more irregular, right? When we talk about some smooth surfaces, it is essentially the copolarized signal that is helping us. But when we are talking about very irregular or rough surface, we are talking about a cross polarized, that is horizontal vertical or vertical horizontal. These high values will suggest a very complex structure, maybe very dense vegetation with a different canopy heights. Okay, so that is more irregular as compared to such a canopy which has a similar height. So the complexities of this surface will be minimal. Whereas when we talk about a deciduous forest which has different types of different heights of canopies, we're talking about yet again a different kind of environment here, and this cross polarized signal is very well able to pick it. Then we are using both, that is the co-polarized as well as the cross polarized lights, depending upon what we require in order to be able to interpret it habitat, right? So very low VVVH indicates smooth water, whereas very high VV will suggest urban double bounce scattering mechanism. What we say double bounce is essentially to do with two different heights, right? So we have two different smooth heights. For example, one is buildings which have a smooth top and they are reflecting nicely. So you have very low VB or VH kind of component, and then you have a lower elevation, that is the ground, which is also essentially maybe paved or tarred or something like that, and that is also a smooth surface. So we can also apply this kind of understanding in even natural habitat. All right, what exactly those cases are, you maybe you can give me some indication of what comes to your head when I say two different smooth surfaces of different heights. let's just compare these two, that is the optical sensors and the radar sensors, that is microwave sensors. Let's look at what are their advantages and what are their limitations. So first let's talk about the optical advantages. Optical sensors have these advantages in the sense that they are rich spectral details for vegetation health. Vegetation health can be very excellently monitored and understood using this spectral data. You have data ranging from green spectrum to red to near infrared, and you are able to very well interpret what is the health of the vegetation. Whereas when it comes to SAR, it cannot do that. It cannot talk about what is the health of a given vegetation, but the optical sensor can excellently do it, irrespective of whatever limitations it has. And also it can make different color composites, so band composites, or also it can make, so it is able to help us in distinguishing between different types of land use, land cover. If it is urban region, then it is going to have a different spectral signature as compared to that of vegetation, as compared to that of water bodies. So all of them will have different spectral signature, because of which we are very well able to make use of the color composites in order to identify these different types of land use, land cover, or within the same kind of land use, land cover, we can further discriminate it, and so on and so forth. Then there's a strong class separability between shortwave infrared and near infrared, which essentially the microwave cannot do. We have to understand how a near infrared is different from shortwave infrared, and to go a little beyond, we should be able to understand how a near infrared is going to interact with a given feature, and how the shortwave infrared is going to interact with a feature. For example, when we say water bodies, no, when we say water bodies, near infrared near infrared energy is essentially warmth carrying energy. So when we go out in hot sun, we feel a little warm, isn't it? We feel a little warm. Why that warmth is there is because of near infrared. Near infrared energy essentially brings warmth to our planet, to our atmosphere, to our hydrosphere, to the biosphere, to the lithosphere. So whenever this near infrared energy falls on a body of water, water quickly absorbs all that warmth. Right? Now, water body will continue absorbing near infrared completely without letting anything escape from it until it reaches 100 degrees centigrade. Only then, whatever energy comes to it will be reflected back, because it has already reached its boiling point. But does that happen in nature? No, it doesn't. That means what? All throughout, whatever near infrared comes in contact with water bodies will be completely absorbed. Whereas when it interacts with the land and land dwelling features, it is going to show some reflectance. For example, if humans were to, you know that humans can see only the visible spectrum, isn't it? We do not see beyond these Vibgyor colors, that is violet, indigo, blue, your green, yellow, orange, red, right? We do not see anything beyond that. We don't see near infrared. But if humans were to see near infrared, no, we would have not seen vegetation green in color. Okay. So when this Vibgyor color falls on vegetation, green is the only color that reflects back, whereas everything else is absorbed by the chlorophyll pigment. However, if we were to be able to see near infrared, you will realize that vegetation reflects much better in near infrared than that of green. So if humans were to be capable of seeing near infrared, vegetation would have not been described as green. It would have been described as near infrared in color. We will look into what exactly how it looks in terms of the band as well, and you will be able to appreciate that fact even more after that. So beyond that, you will, it is very excellent, that is, the spectral bands, sorry, the optical sensors are very well able to help us in deriving this NDVI, that is normalized difference vegetation index, or enhanced vegetation index, or yes, correct. So sounds it is definitely interesting, and it will be more clear when we exactly look at the bands, and you will be able to more appreciate these spectral signatures. Correct. And then NDWI, that is normalized difference water index indices. These are the ones that we can calculate using a spectral band, using spectral bands only. We cannot do it using synthetic aperture radar or the microwave sensor. Microwave sensor is not able to do it. Then what are the limitations of these optical sensors? Cloud. If there is some cloud, if there is some haze, then it will interfere with our signal, and the signal will be will carry a lot of noise, will carry a lot of a lot of data will be hidden because of these clouds and because of this haze in the atmosphere. So atmospheric disturbances are very much influential when it comes to capturing any data using these optical sensors. Then daylight dependency, at night it cannot function it because it is a passive sensor. It has to depend upon sun shining bright in the sky. So if there is no sun, then what is happening? We do not have data to rely upon. Then atmospheric correction requirement, that time whatever atmospheric correction that we do, it still remains that no, we cannot remove the entire cloud, isn't it? We will have to get rid of the data altogether, find another data. So that is a problem. Atmospheric correction is also a problem. We cannot do it to the maximum extent such that we remove all the haze or all the cloud or anything like that. We cannot do that. Then coming to this SAR, that is microwave data set, it is operational in all the weathers. If there is some cloud, it will still penetrate and it will collect the data, because cloud it doesn't see the cloud at all. Then at night also we have some data. It is not necessary that it has to be daytime. At night also we have some data. It is very sensitive to moisture and the structure of the feature that we are observing. It is that is the microwave signal is modified by the moisture content present within the feature or the structure of this feature, which yet again is very beneficial for us to understand the topography of a given environment, maybe the canopy height, whether to differentiate. There's a cloud cover, and we are not able to get any optical sensor data. We have a SAR data. We are able to differentiate between grasslands and deciduous trees or deciduous canopy, right? So these kind of advantages it offers. It's excellent for flood and wetland mapping. We can very well map which are the regions that were under flood and which are the regions which are wetland. Essentially, because when we talk about wetland, we have two different heights. One is of some canopy and the other is that of the water body. And even more so, there are some regions of the wetlands wherein the vegetation remains submerged and you have a smooth surface of this water body, so we are able to detect that particular topography and be able to differentiate between the two. Then soil moisture detection capabilities. This microwave data can be very well used to understand the soil moisture, how the soil moisture changed. If you want to perceive, understand when the drought condition is coming, or where a particular region is more susceptible to drought kind of conditions, or where there is active waterlogging happening and things like that, expansion of wetlands or shrinking of wetlands. This is something that can be very nicely mapped with these microwave bands. What are the limitations? Speckle noise effect. You will see some pepper like or salt like disturbances within these images, within this data set. That is very slightly difficult to be removed. We are not really going to deal with how to remove them. However, we will see how to obscure them, and from the very first itself try to minimize them and things like this. So speckle noise means there you will see some minute grains which are which can be perceived as a textural change within the data set, and that is a noise essentially. So complex geometric distortion, there could be some geometric distortions that you will see within the sensor captured data. Then less intuitive interpretation, that means humans do not have a huge control on how to perceive a specific kind of topography that we see. So if we see something that is smooth, the machine is going to tell us that it is smooth, and we are at a least choices to it is not. So even if you want to say that it is not, but this is what the signal says, that's how it is. And then we might have to find out why exactly it is not showing us a rough signal which it should otherwise, and it is showing a smooth surface and things like that. Then, so there are different targets within a habitat. There are different targets. The essential ones are the vegetation, the water bodies and the urban areas. When we say vegetation, we look at how vegetation reflects or responds to optical sensor and to that of a microwave sensor, that is a synthetic aperture. Every time that I say microwave sensor, here essentially we are talking about a synthetic aperture radar or radar data, right? So high near infrared reflectance from leaf structure, because I told that the chlorophyll content is able to reflect much better in near infrared as compared to that of green, such that if humans could see near infrared radiation, we would have not seen vegetation green in color. We would have seen it as near infrared in color, whatever that color is. Maybe it must be deep red or something like that, I don't know, but we must have seen vegetation reflecting very excellently near infrared, right? No more green. So when it comes to optical near infrared reflectance from leaf structure, it is able to tell us what is the structure of the leaf. Then red will be absorbed by the chlorophyll much more better than that of green. Green is essentially not taken by chlorophyll, it is reflected. That is why it comes to our eyes, we perceive it, and that is how we see vegetation as green. But you will see when the vegetation slowly starts withering, no, it becomes yellow in color, then it becomes orange, then it becomes red, then it becomes brown, maybe the darker colors, right? That is why, because the chlorophyll is dying. Chlorophyll is the only sole component which is responsible for imparting a green color. That means what? It is not able to absorb green. It absorbs essentially red. So what it does, it reflects back this green. Is not able to absorb green to such an extent. Only 30% of it is absorbs. That is why we see vegetation as green in color. So red is absorbed. So these are things which essentially a optical sensor can tell us. Then comes these water bodies, sorry, we have to talk about the microwave sensor. So volume scattering increases cross polar signals, moisture affects backscatter intensity. When we talk about vegetation, this is how the microwave sensor is going to help us. It is going to talk also about how rough the surface is, and it is also going to talk about what is the moisture content. For example, if we talk about um, some phreatophytes, if we talk about some phreatophytes, no, because maybe it's a waterlogged region, that kind of habitat. So what you will see is that the moisture content within the vegetation is high, whereas that vegetation which is away from the wetlands or does not really require a constant supply of high amount of water or something like that, then you will see that it has a lower content, moisture content. So this is how SAR will help us. Then water bodies, low reflectance in near infrared. I told you that the near infrared is completely absorbed because it is warmth carrying energy, solar energy. So what happens, it quickly gets absorbed by the water, nothing comes back to the sensor. That is why sensor is essentially an optical sensor that senses near infrared, is essentially blind to water, it doesn't see water at all. That is why near infrared is used to discriminate between land and water bodies very precisely. With over 99% of accuracy, we can differentiate land from that of near infrared. Then it enables water body detection because water is absorbing it completely, land is reflecting on the other hand. Then coming to SAR, it's smooth water acts as specular reflectors. So when there is a smooth water body, it tells us that the water body is stagnant. Okay, and we are able to interpret that it is a water body, creating very low backscatter. If because whenever some incident radiation comes, it directly goes back, and there is very less of scattering. So whatever comes in that same polarization scale, it goes back, right? I hope many of us are aware of these polarized glasses, no, I will say the polarized glasses. If you wear them, then the amount of energy that comes to your eyes is minimized, and also in a certain angle only it vibrates, right? So you are not able to see those components which to be able to see them, you will have to have a wider scattering angle. I don't know whether you have seen something, if you go for buying this polarized spectacles or something like that, no, they show you a picture and they tell you, do you see a plane there, and you say no, I don't. But then when you wear these glasses, you suddenly see this plane flying in that particular airspace, like that. Okay, so that is to do with just visual thing, no, about polarization of how the light is allowed to vibrate, and in a certain vibration direction you see those things, and if you change the angle, then you don't see them, because essentially they cannot be perceived with that much of scattering angle and things like that. Then the third component, which is very essential for habitat mapping, is urban areas. Optical high reflectance in visible and shortwave infrared bands. That is why you require it high reflectance. It will show very high reflectance in near infrared, because it is already hot enough, no. Urban areas, these concrete jungles, they are already hot enough, so whenever solar energy comes to them, they are also painted white and so on, like that. So what happens, whatever energy comes, whether in visible spectrum or in near infrared, goes back, it gets reflected back. Okay, so that high reflectance of visible as well as infrared region helps us in identifying them when it comes to optical sensor. But when we are talking about synthetic aperture radar, that is a microwave sensor, strong double bounce between building and the ground. So building is at a higher elevation, the top of the building is at a higher elevation, again a smooth surface, and then the ground, which is also smooth but at a lower elevation. So this creates a very distinct differentiation between the ground and the and that of the building, and that is how you are able to identify them. No, we are not really essentially going to talk a lot about the pre-processing requirement. When we talk about optical processing, use level 2 surface reflectance data products directly. If you want to get rid of any cloud cover or something like that, then use this SEL or QA layers, which are used for masking the shadow and identifying which are the cloud affected regions. So just remove them and only use whatever is without any cloud, or maybe find some other data. That is another way of looking at it. If you want to mosaic two three different images from one point to another, then that is coming under pre-processing. When we talk about SAR processing, thermal noise and border removal, if there's any border that is ambiguous to the data set, nothing related, or nothing that corresponds to that kind of image or kind of region that you are looking at, then you have to remove that. And the thermal noise, if there is any, then you have to remove that. The calibration has to be applied to this coefficient of backscattering, that is sigma naught and gamma naught. That naught should come as a suffix. Okay, please keep that in mind. um, I'm really sorry for whatever efforts that I have not put in, but it is sigma naught, it comes as a suffix. Okay, sigma naught and gamma naught. Then speckle filtering, we were talking about this salt and pepper kind of noise that we see in this sentinel one, that is microwave sensor, that is synthetic aperture radar. So in order to take that off, we apply something called Lee or refined Lee calculations or pre-processing techniques. If we have time, we will go through it. And then comes the terrain correction, that is again applicable to these microwave sensors, essentially the DEM corrections, what we say. So apply radiometric terrain corrections and use high quality DEMs like that of SRTM or LOS pulsar. So the LOS pulsar is essentially a synthesized 1 meter resolution data set. It is not directly only based on the satellite captured data set, also converted to decibels for visualization. So all that comes into picture. Feature engineering for classification. What exactly is feature engineering? It is wherein we take into consideration a specific kind of data set. We look at what are the different things or different kinds of data sets or different kinds of parameters that we can extract out of it. For example, when it comes to optical sensor, we have different types of bands that are available. For example, here this is I think Sentinel. Sorry, this is Landsat 8, I believe. Okay, and Landsat 8 or 9. So these are the different types of bands that are sorry, band 12. That means it is Sentinel. Okay, so these are the bands that are available. These are primary bands that are available that comes along with the data set. And from using these bands, you can derive several indices like NDVI, EVI, that is Enhanced Vegetation Index, Normalized Difference Water Index, Normalized Burn Ratio, then moisture stress index, and SAVI, that is soil adjusted vegetation index, I believe. And then seasonal composites, median and percentiles also you can generate using these data sets. Then for SAR feature, backscatter can be used to understand both the co-polarized as well as cross-polarized signals, VV, VEH, or HV and HH, and things like that. Ratios also we can work out with VV by VH, that is co-polarized by cross-polarized, and also differences we can work out in order to be able to understand the topographic changes. Then some textural measures, what kind of texture a particular given kind of land use land cover or the habitat has, right? And then multi-temporal composites, so we work over a scale, a time period, let's say about flooding, before flooding, during flooding, and after flooding, how the flood started receding, which were the areas that surfaced first. On in case of habitat mapping, essentially to do with shrinking or expansion of wetlands, or maybe you are able to see suddenly somewhere phreatophytes are coming up because of waterlogging and things like that. All that comes into picture. Now, how, when do we use which kind of data set? We'll quickly go through this. I think we are done with this particular PPT. We were supposed to, I was thinking that we will finish by 8, but then, however, it has taken a little longer. All right. So choose optical sensors when you need detailed spectral information, that is to do with the health of the vegetation, or the moisture content and things like that. Sorry, not moisture content, but health of the vegetation. So you need detailed spectral information for species identification. Or these species are essentially vegetation. Okay, we are not talking about um, faunal species. We are not talking about faunal species, because we can find some proxies related to the faunal species, but not when it comes to floral species, we are able to identify them to a large extent. So we need detailed spectral information for species identification, vegetation health assessment, or cartographic clarity. So what is a topography, no? In land cover mapping application, so that is where we will use these optical sensors. Then if your work is something like you are working in persistently cloudy regions, which are mostly like Tamil Nadu or the Kerala coast, which are very close to that of the intra-tropical convergence zone, where you see a lot of cloud cover, very difficult to find clear images, because it is always mostly covered by some clouds. So if you are working in such a region which are very cloudy, then, or if you are mapping floods are essentially when the skies are cloudy, isn't it? Or if you are mapping wetlands or requiring structural and moistural sensitivity regardless of whatever the weather condition is, then you go for using SAR. Then you combine both if maximum class separability and robust classification. If your agenda is to find maximum separability between different types of habitat, in this case, because we are concerned with that, then for the classification you combine both, and that is exactly what we are doing during this particular course. So stack optical indices with synthetic aperture radar and texture features for optimal habitat discrimination. You should be able to discriminate between one vegetation to that of other. Okay, the most reliable habitat maps will fuse both these technologies, that is the optical spectral chemistry will reveal what it is, while the synthetic aperture radar will reveal the structure and the moisture, that tells you how it has been formed, how it is built. Okay, so we will get into the hands-on session. Besides that, there is absolutely nothing in this particular PPT. That's just about the hands-on data download sessions, and that we will be going through now, and the data discovery, how to discover the product, how to select, what is the selection criteria, that is you have to look at the cloud cover, then which window essentially you are looking at, whether summer or winter or what, then path rotile, and then the polarization that you are looking at, the orbit ascending or descending from north pole to south pole, or from south pole to north pole, so that is ascending or descending orbit. And the product level, that is whether you want to go for raw data or you want to go for something that has been already processed and made available for you, and you can directly go for using it, right? And these are yet again the different types of portals from where you can download it. We are going to pay more attention to something called a Copernicus data space or Copernicus Data Hub. That is one that we are doing, because essentially regarding the other two, I think I have already given you some videos. Some of you who had joined that particular group, if you have not, then I will share yet again the videos with you all. All right. Okay. So we will first begin with the hands-on, and then we will take up a more concrete discussion, right? We are here together for a very long time, so don't worry even if I did not ask you to introduce yourself, but then please be prepared to tell me why exactly you joined this particular course and what are your expectations, because that will help me in if I want to do any modifications in the course to meet with your requirements, then I'll be able to do that, right? All right. So what you can do is you can go to Google. Okay, let's be a little self-dependent rather than independent. So what do? Just come to Google. Okay, punch in there Copernicus data space ecosystem. Okay, just punch in Copernicus data hub. Also, you can try Copernicus data space ecosystem or Copernicus data hub. Okay, anything, and you will see this particular site. When you go there, this is the kind of interface that you see. It is dataspace.copernicus.eu. Okay, the data comes from European Space Agency. Uh, Take capture. All right. So when you reach this particular interface, you go for exploring the data. Okay, we want to explore the data before we download it. So when you come here, you will be asked to log in. Okay, you go anonymously. You can only browse through the data. You are not able to download the data. So go ahead and log in. You will be asked to make an account because we don't have one. We will go for registering. Very quick. Okay. My first name is Diksha. My last name is Karapurkar. I come from this village called Karapur. Then my email ID. Okay. Give it some password. I'm giving some strong password that the system itself is suggesting. Country has been detected. Type of user, I am a natural person. A research and education organization. Okay, you can say that. Then thematic activity, you can choose what exactly you are trying to do with work with. Environment, I want to say marine environment, maritime affairs and fisheries. Purpose of use, education. Okay, I accept all the terms and conditions and privacy policy. Give the permission to contact you at the email address provided during the purpose of possible user service. Okay, if you want to send me some service, do send me. I'm also interested in accessing Copernicus contributing mission data. Okay, okay, yes, I am definitely okay, fine. User category, I am public. Company institution, I am from Pravinya Research. Service project, C3S, I can say C3S. Okay. Climate change, something C3S. I hope you know what is C3S. It is climate change. Only I'm forgetting C3S. What is the full form of it? I'm accepting. Subscribe to CDS monthly mailing to receive the latest updates in your mail. All right, let's register. Okay, don't ask me for more details. Let me register. Have I missed something? No, I have not. That required fields. So what is that required field which I have not marked? Okay. Oh, now almost ready. All right. Stay informed. Registration authentication. All right. So I will. There must be a mail. Thank you for signing up. I will have to go to my mail. Let me go to my mail. There must be something, some mail waiting for me. That is to verify. All right. I will verify my email address. Okay. Very quick it is. Unlike that of yours, Glovis, so some of you might have tried making an account on. Yes, C3S, that is where, Copernicus climate change, some data sets that they provide. I'm exactly forgetting the full form of it. I can definitely revert back to you what exactly it is. They make you available some data set pertaining to climate change. All right. Welcome to Copernicus browser. Okay, all this I don't want to see all this again. So I have been logged in. That is how I know that I've been logged in, because my name reflects over here, Diksha Karapurkar. Okay. So once you have this, you're good to go. Let us go ahead for searching data set. Okay, so you will see sentinel 1, sentinel 2, sentinel 3, sentinel 5, sentinel 6. All the different types of data sets are over here, whatever sentinel data sets that you require, because sentinel data set is coming essentially from the European Space Agency. Now I have to mark my study area that I'm interested in. So if you are able to identify it simply like this, no, then do go ahead and identify it, because there are different, names of the places that are shown here. Also, that you will see state boundaries also. If you zoom out a little, then you will see state boundaries as well. But then I'm essentially looking at a typical study area. So what I will do is I will go to this polygon and I will take this particular rectangle such that my cursor will change into this plus sign. Okay, so now what do? I find a study area that I am interested in. Okay, and what do? I make a box around it. Okay, I make a box around it. Okay, so use this left button on your mouse to select a region of your interest, and then if you want to move it a little, you can do that. Okay, depending if you want to adjust it, no, then you can definitely do it. Okay, no problem. So once you do this, now you're set to go and give your requirements. What are your requirements? I want to download sentinel-1 dataset. Okay, just look at this, what exactly I'm doing. Okay, I am interested in this level 2A data set, that is sentinel 1. If I'm downloading that, I'm interested in level 1. That is, I'm not interested in level 0, which is raw data. At times, in some satellite data, level 1 is raw data, and in some level 0 is raw data. Okay, so when it comes to the sentinel, level 0 is raw data. Okay, level 1 is processed data, level 2 is further processed and derived data. So I'm interested in this level 1 grid data. Okay, I'm interested in this level 1 grid data. This is the one that is best suitable for identifying the topographic changes, and that is why I'm downloading this. Okay, read a little about different types of these data that are available and what are their purposes to be used. But level 1 grid data, that helps me in identifying the topography or the surface structure. That is why I'm going for this. In fact, all of them are same, only the formats are different. So I'm going for this gridded data. Okay, that's all. So Sentinel-1 has three different satellites: Sentinel-1A, Sentinel-1B, and Sentinel-1C. So there are three different satellites that have, succeeded one after the other. So I'm fine with any. I'm good to go with. So I have chosen which kind of data set do I want. I scroll down, I get something called time range. I want to see for which particular time period do I want to download the data set. So I am essentially more interested in identifying some data set for the month of January, because I'm essentially thinking that there might not be thick cloud cover, no, that the even a microwaves won't be able to penetrate. If it is too thick, then microwave is not able to penetrate, or that it gets distorted. A lot of problems will come with it. So I will go for January. So January 1st of 2025 until that of April, I'm expecting to be less cloudy. So maybe 30th of April, or I think I should go for only January 31st. So let's see how it goes. Okay, January 1st to January 31st of this particular year itself. And then what do? I go search. I simply click on search. As simple as that. Okay. Let's wait for the data to be populated. Now you will see that some data has come. If you wait a little longer, then you will see some preview over here. Okay. So you hardly see any cloud cover as such over there. Okay, and then you can find out which date you really want the data set for, or that which particular data set is covering maximum of your study area, right? So I see here that this particular data set was captured on 2025, that is first month of 2025, that is January 26th of 2025. If you are not able to read and understand the nomenclature of this data set, that is the ID of it, scene ID of it. The scene ID tells you exactly which particular data set it belongs to, which particular satellite, what kind of data set, on what day it was captured, and things like that. Its path and row and things like that. But then if that you are finding a little difficult, after some time you won't. But look at this sensing time. So sensing time is 2025 first month, that is January 26th. And then it also gives you I think this is time. Okay, this seems to be time. So 56th minute of the 0th hour. Okay, so that is what it does. So once this is done, you can have just have a look at what exactly it is, visualize it. So it will be populated over here so that you see what exactly how it is. Okay, it seems to be covering the entire region of my interest, right? So what I will do, I will yet again go back to search, and this is the data set, that is 2025 January 26th. I'm ready to download it. So what I will do, I will simply click on this particular button, that is download button. You see a small icon there, and then this data set is 1638 MB. So what you can do right now, just start so that it runs, let it come to 1%, and then stop it. Okay, later whenever you have enough space in your device and you have enough data connection, then you can download this data set. But make sure that you download it, because it is more important that in this particular coursework we are able to reproduce what we do. Okay, so reproducibility is very important when it comes to any kind of research work, I would say. Anytime somebody asks you how did you get this, you should have all the data back with you. You should be able to show that this is how I got it. Okay, that somebody else should also be able to reproduce your work, and that is very important when it comes to any kind of research, whether it is your final year thesis research or master's degree, or a PhD, or any kind of research, a small mini project as well that you are doing. Often that is something that is overlooked when we deal with Google Earth Engine, and then we will also deal a little bit about Google Earth Engine as well, see how exactly it goes and things like that. So this is how you download the Sentinel-1 dataset. I will stop it for now. Okay. Now this I'm able to download. Let us go back. Okay, let's go back. Only I have to go back to the search. Okay, I have to go back to the search. So I this time I want to download Sentinel-2 dataset. So what do? I click on Sentinel-2. I want to download level 2A products, which are, yes, the okay, all right. Okay, so this time we are downloading the multispectral dataset, that is Sentinel-2. So I'm going for level 2A, which has already been corrected for the atmospheric correction. Then yet again I go to the time range. I have already set it from the 1st of January to 31st of January of this current year, that is 2025. Let us go ahead and search. Oh, I must have picked the data. Oh, yes, it is already set. Good, good for me. Okay, so now you will see that there are four tiles which are covering my study area. If I hover mouse pointer, then you see that there are four different tiles, right? And then in between you will see that the rectangle or the study area of interest that I had marked is popping out over there with its vertices, with white balloon balls that are floating there, right? So now if you come here, you will see that different data sets which are available over here. You will have four tiles. Okay, the repeativity is 5 days. You will have to identify one such data set which doesn't have any cloud cover. You can scroll all the way, just find out these are the ones that I have total 20 results, and all of them they are showing. So I don't have more data set there. This seems to be cloud cover. Some problem with this is only very little of my study area is covered, and here also the same case. This seems to be a good data. Okay, this seems to be a good data. Let me visualize it so that you will be able to see it over here. It might not cover the entire study area of my interest, but data is still loading. Wait for some time. think it has loaded. Okay, so now you see that this is the data set that I am downloading. I think I'm pretty fine with it. These are the different indices that are already made. The machine has already, I mean, the system has already made it. It has been pre-processed. Some NDWI, that is normalized difference water index, you'll be able to see that it differentiates very well between the vegetation and the water bodies. So that NDWI, if I want, I can directly download it. Then there is NDSI. I'm not really aware what exactly this NDSI are, because there are different types of indices. Could be salt indice or could be anything. Then you have moisture index, you have NDVI, and many different other things are already shown over there. And I'm quite happy with this particular data. So I go back to search. I yet again locate where exactly it is. So where it is here. I'm good. I can download it. Okay, so I will go ahead and click on this download button so that it starts downloading. If you want to see what is the size of it, it is 979 MB. Okay, so I will wait until it goes to 1 or 2%. Yes, 1%, that means it is downloading. I have to have solid internet connection to be able to download it, and a little better one so that I download it pretty quickly without wasting any time and things like that. So I will pause it for now. Okay, these are the two things that we need to do by the time we meet next time, that is coming Friday. In another 2 days, make sure that you have these two data sets that are downloaded, and you will have the video with you. I will be sharing the video with you. So that is to do with the hands-on session. I would also want to quickly show you how to download Lancet dataset from USGS Globis. Okay, so let's quickly look into that. USGS Globis. Now this is a little difficult. It's a little tedious. You know. Portal to make an account on, that is there, but just have a look at it. It's very user friendly. Once you have an account, you're good to go with. Okay, so this is the interface that is in front of me. I will have to log in first. Without logging in, I don't get to download any data set. So I have already made my, sorry, I've already made my account on this particular portal. So I'm just punching in my credentials in here yet again. Okay, and then I sign in. This should be quick. This is for downloading Lenset. 8 and 9 both you can download. Okay, so I will first select which area I am interested in. So what I will do, I will bring this cursor over the region that I am interested in. So let us bring it over the study area that I am interested in. If you are not able to find your study area because it is not coastal, then you can click on this three-leaf map, and from here you can punch in whatever your latitude longitude is, and then you can jump to that particular location. Okay, so that will be fine. Come to this left hand side panel that reads interface control, and below that you have selected data set. So click on this plus sign, navigate to Landsat 8 and 9 because that is exactly what we are trying to download, and add selected data sets. And after that, if you want, you can also add some common metadata filter which includes also acquisition date. So let's say I want to download it for um 1st of January of 2025, sorry, 2025, and to 31st of January 2025. Okay, and then I'm adding this filter and close it. You can add more filters like cloud cover and things like that if you want, but see, the scene navigator opens up. If that doesn't open up, no, if the scene navigator is not there, you will see a small steering wheel kind of icon over there. You can choose it, and then you will see that some data starts popping up. Okay, so wait for the results to load, and then identify one such data set that doesn't have any cloud cover, and then go ahead and download it. Okay, so yes, LULC forms a very important part of habitat mapping. We will have to cover it. uh, in fact, I would say that habitat mapping is same as that of land is land cover mapping, only that you take into consideration multiple different factors as well, climatic as well as biological factors. Okay, so I can simply click on this download button. Now here I will get multiple options, of which I have to download the product bundle. Okay, the product bundle will come to around 900 or up to maybe 1000 MB or something like that, a little more than 1 GB. So I can simply click on this particular request download button. One more pop-up will open. Don't close it down, because if you close it down, then the data won't get downloaded. So wait until it directs, or the downloading reflects back. Okay, so this is all about the hands-on session. Please practice it. I will send some videos as well to you, to be able to download dataset from Earth Data and USGS Glovis as well. And this is where I rest what I wanted to do for this particular session, the PPT and the hands-on. It is very easy, don't worry. I might have gone a little fast because it's the first day and I started with a PPT that consumed a lot of time, which was very much necessary, and I had to do go ahead with the data downloading in here. So please bear with it, because the data set, yes, see, you see that it has started downloading. So now I will be directed where to save it and things like that. So let me quickly show you how I'm going to store it. Okay, I come to my desktop. You can go anywhere. Okay, so I come to my desktop, and here I already have many different uh, folders. I will make a new folder and I will call it habitat mapping. When I say habitat mapping, there are two words, no, habitat and mapping. To separate these two words, I'm using an underscore. Okay, keep this in mind. Every time that you make any folder, any data, make sure that two words are separated by an underscore. Have that habit everywhere, no matter where. Okay, so I'm writing habitat mapping, which means that I know whatever data that I'm going to generate, I'm going to download for this particular purpose, I'm going to store it within this one folder. Okay, so let me go in this particular folder, that is habitat mapping, and I'm going to sort this particular. Yet again, I'm making one more folder and I'm calling it raw data. Okay, I'm calling it raw data. No, sorry, I will call it satellite data. Okay, I'm going to call it satellite data. Yet again, satellite is separated from data with an underscore. I made a new folder, and let me save this Landsat file over there. Okay, so this is how you are going to save your data set. This is how you are going to name your files, your folders, and make sure that all of them are sorted. No matter when you visit them, everything is sorted, kept right in place, and that the names are very well briefly described, such that they tell you what exactly they mean, or what is the purpose that you downloaded them for, right? So yes, so that is it from my side for today. Let us interact a little so that we discuss what are our expectations, right? Let's look at the questions that we have. Kaushalika is asking us, there's a question that they have asked: can we use mixed data types for differentiating between vegetation within evergreen forests, where trees are diverse but close canopies vertically and horizontally similar? Yes, definitely. We can use mixed data essentially to differentiate between the health parameter of this vegetation, because even though they might be having the same height or the similar canopy, maybe deciduous of the same height, then in terms of the chlorophyll content, they will be different. Or in terms of their leaf index, the kind of leaves, what is the surface area of their leaves will be different, or that the chlorophyll content will be different, right? Even that there might be some species which shed during winter, so we will be able to differentiate between them during the winter season and things like that. Right. Yes, they're also asking. This is a little fast for me and my internet, but I'm assuming time to do. Yes, surely you will have enough time to this, right? Yes, yes.
Um,
Kaushalika, would
can
you
I?
like to
Yeah,
speak to us? Yes, please tell.
yes.
Please unmute
It's
yourself.
also it's about my question again. Um, so can we also use a moisture data to differentiate between species in an evergreen forest?
Can we use what kind of data?
Moisture. So I'm
Yes,
assuming that trees will have. Yeah.
Yes, correct. So SAR data we can use to differentiate between the kind of the level of moisture that is available in a given species for a given period, and based on that as well we will be able to differentiate between the species, that is essentially the vegetation species. Correct. What you have
Uh,
understood is correct.
thanks. Yes, yes, thanks. And since
Okay.
we are since we are still on me, can I just ask another question? Sorry,
Yes,
others.
yes.
Um,
Yes, dear. Please go ahead.
uh, so um, so I had a question about how much in detail can be within the land bit. Can you like actually go up to a rock and then define that with remote sensing?
The
Maybe a
kind
biggish
of
rock.
rock you are asking?
Yes, as in not geologically. I mean, if there is a say for example there is a plateau and you have some rocks defined on that plateau. Uh, is it possible through remote sensing to actually see different rocks like that?
We
So
are
what I'm getting
able.
at basically is differentiation. Yeah.
Okay, I got your question. You want to understand whether even the rocks can be differentiated between one kind to another, right? So, different
Yes.
rocks, I would say, have different amount of clay content which is present in them, also iron content which is present in them, or the moisture content which is present in them. And yet again, these remotely sensed data can help us in differentiating between the clay content, the type of clay, the moisture content, and yet again the ion content, which are the primary proxies in order to be able to differentiate between different types of rocks.
Right. Thank you. That answers my question. Thank you so much.
Yes, all right. Okay, so we have some questions coming from Dipti, I believe. uh, yes, we are going to cover some parts of land use land cover, definitely. In fact, habitat mapping is also a kind of land use land cover mapping. At times it is that the habitat is being used by some other animals other than humans, and we try to look at the proxies. Yes, when it comes to classification between different types of vegetation, yes, that is at the center of our agenda for this particular course. Then yes, we are going to cover that. Yeah, that's fine. Jayesh is saying that we are pretty fast in the hands-on. Um, yeah, that we will be lagging behind. Okay, no worries. As I mentioned no earlier, that today I might be a little fast with the hands-on, because essentially some part of it has been covered within the videos that were shared with you all. Uh, and that is why we just wanted to finish it in time, right? That you don't spend a long hours with me. That is why we have tried to go a little fast, but don't worry, the recorded session will be with you, so there should be no problem. All right. Okay, so I would want to know what are your expectations from this course, and why you joined this particular course, right? I will take a few of your names, and some of you can voluntarily tell me how it is. Let's wait for 2 3 seconds so that some of you voluntarily speak about these two things. You will hear me keep quiet. The questions are why you joined this course and what are your expectations from this course. Let me wait for a few seconds.
May I?
Yes, 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 sir, Sanjay. Please speak.
Hello, am I audible?
Yes, audible. Oh,
Oh,
sorry.
sorry.
Audible.
Audible.
Yes,
Yes,
you're
you're
audible. I'm
audible.
so sorry. I'm saying that we have two questions: why you joined the course and what are your expectations. Please go ahead.
habitat assessment is very, very crucial in certain part of it, because the conventional understanding is that elephants should be there in that habitat, but they are not using it. There would be other factors also other than quality of habitat, but that is one thing need to be scientifically studied. And definitely, we often have issues in terms of doing it in a primary way, meaning going to, because it's a huge landscape, it requires a lot of fund, time, energy, and resources, a right set of resources, which is very difficult to get often. So this becomes one of the methods which might be cost effective and time effective. So from that point of view, I have joined this course to understand that if I have to do it myself or I have to do that, how do I inculcate that skill set where I need to know what to be studied and how it need to be studied, what should be the credibility. For example, you talked about various indices, but if I'm using a particular data set, within that, if I'm using certain bands, what would be the credibility? Why that certain brand? Why that particular data set? And tomorrow that wouldn't be questioned and challenged, So how to read between those finer gradients, So that's somewhere the expectation I have. I hope I wasn't too confusing.
Yes, yes, you were audible. We could hear you, and that is rightfully said that whether a given species is really using it, that is the quality of the habitat is very important when it comes to finally putting those maps forward with the highest validation. We will have to validate what we have mapped, whether that particular habitat is really being used by the species or not. Have we understood you rightfully, sir?
Yes, yes, ma'am. Yeah.
All right. Okay. So here I would say that I will have to take a little care of finding some secondary data about whether a given species that is representative of a particular habitat is really seen or observed dwelling in that particular habitat or not. All right. That is considered. I've taken a note of it. Thank you so much for sharing your views. Thank you. All right. So anybody else would like to speak to us?
I'm sorry, I'm just, I just want to give uh, uh, insight that makes my problem maybe more understandable. For example, elephants like to be in the secondary forest, which is more of a generalist, which would have shrubs, herbs, grasses, and they would not prefer to be in evergreen forest. So that's one example if I give. So that is something which is almost kind of I would say a universal truth. So they would go to evergreen forest, but they would not stay there for all 365 days. So if that is being a hypothesis, if that is a being a truth, and then we say we study then, using different data sets, that what kind of quality of habitat a particular project site has using different data sets, rather than going on the field and doing that for almost 2 years. By the time the whole sense of the time is gone, vis-a-vis using different data sets and studying that quality of habitat in non-evergreen forest, if I had to put it that way.
Okay. Yes. Okay. I think this is understood. Thank you. Thank you so much.
Thank you.
Nice to hear from you, sir. Anybody else would like to share their views?
Hi, I actually more have had a doubt. I think it was clear from my questions as well. I've been trying to teach myself about GIS through YouTube and everything, but it's been a bit confusing when it comes to LULC and vegetation differences, because I only have, it's like you have the resources, but I've been having difficulty with the application part. Like we go in the field, we are mainly tracking migratory birds. So there I can make an observation taking the GPS coordinate that here there is certain kind of vegetation and it stretches from so and so. And if I'm tracking electric poles in certain wetland areas, so I can take all the coordinates. But when it comes to mapping it out on the map, it's easy to feed the direct coordinates, but when it comes to classifying them, like looking at the map itself, I'm not able to classify the vegetation. And then it's like, I know from what I saw on the field that so and so certain area looks like this, but when it comes to pinpointing it on the map, I'm having different, like, difficulty classifying it. And even in LULC, when I'm trying to do it by myself, it's like you keep on feeding the data that this area is supposed to be so and so, this area is supposed to be so and so. And after like 30 minutes of doing it, instead of, the different gradient that you're expecting, I'm getting like one single gradient over and over again. So I had a lot of these kind of doubts that even if you're doing all the correct steps, it's like somewhere or the other you're missing out, like what is going wrong. So I was hoping I'm able to resolve those doubts through these sessions. Thank you.
Okay. Yes, thank you, Deepti. Thank you for sharing your views. So, I would like to just tell you this now that we are not going to go for an exclusive land use land cover classification. However, what I will do is I will share a video with you which might be able to help you with a generic kind of level 1 or level 2 classification of land use land cover. That is, if you want to separate, vegetation from that of dense vegetation from scanty vegetation, water bodies, then built up land, barren land, water, and things like that. So definitely I will share a video with you all. Please remind me if I don't share it by tonight. And Yes, besides that, like I told you, that habitat mapping is also much like that of land use land cover mapping. So I believe that the techniques that you learn through this particular class, you will be able to use them more insightfully in your land use land cover classification as well. Okay, thank you so much for sharing your views. Anybody is waiting? Yes. Kaushalika, please speak.
Yeah, hi.
I hope I'm
So
pronouncing your name right.
it's Kaushalika, yes, that's right.
Kaushalika,
So
yes.
I think the session, first of all, the session was really wonderful. It was fast, but I can understand why. And we would probably have enough time to go through it. But from the descriptions from the previous two people, they're very interesting. Their work. I do not have any concrete reason to take this course up. This is an avenue that I'm opening up for myself. I did come through with my own. I have my own land, and I would like to do some long term monitoring over there using remote sensing as well as field observations. So it is definitely one way of opening up an avenue to study multiple things. I am a researcher in animal behavior and welfare. So as we were discussing, I sort of came up with something that might where this might be useful, and that is one thing is within a zoo context, I might be able to use some of this data for enclosure use by animals to sort of define, how they use it, why they use it. Maybe this will be a data that will add on to it. I'm not so sure, but it's definitely going to open up avenues for me. So that's the reason why I'm here. Thank you.
Yes. Thank you so much. Thank you so much for sharing your views. I wish you good luck. Yes. Anybody else is waiting to talk to us? Shraddhaji, would you like to talk to us? Would you like to share? So often I will end up taking your names. No, if you don't want to talk, you may just keep quiet. Yes,
No,
Shraddhaji,
it's
please speak.
absolutely fine. I was just waiting if someone else was taking the call. Hello, this is Shraddha Mahadik. I'm a PhD candidate from Mumbai University. Currently, I'm not really looking at solving any kind of problem at my end. The work majorly consists of environmental chemistry. But yes, surely I'm looking forward to, sort of hone my GIS mapping skills through this workshop. So yes, and today's session was really, it was wonderful. Thank you so much, Praveen. Thank you.
Thank you so much for sharing your views. I think you will become very excellent at making maps and mapping. That much I can say, because we are going to use a little more advanced ways of mapping. Nothing is difficult. It's basically just a software and some data set that we have at our hand, and we are going to use them in order to achieve our objective, that is of mapping a certain kind of habitat. And there will be different techniques that we use in this process. So you will definitely end up learning a lot, many different types of techniques for mapping. Rather than being just a beginner, we will get to a little beyond that of intermediate level. I would always say that we never reach that advanced level. It's always another step to take. But yes, it's going to be very beneficial to us. Okay, anybody else who's waiting to talk to us? Vishal, would you like to talk to us?
Uh, Hi, ma'am. Hi, everyone. So, my primary motivation to learn this is I'd like to understand basically the impact of linear infrastructure on, say, habitats on forests and wildlife. There's a good deal of ground truthing that we basically do to understand the uh, potential impact of a proposed infrastructure project. So we think that I think that this particular course, the habitat mapping course, and basically using RS and GIS will help us bring more insights into in our study in this work. This is one dimension that we've generally not used before, partly because our understanding of RS and GIS is also not that great. Uh, but generally, we've been relying only on the ground data. We hope that this course will actually uh, bring the RSGIS element into our analysis as well. Thank you so much.
Yes, thank you so much. Thank you so much for sharing. I would I would like to add to that, no, when we are trying to understand how a given infrastructure that has been built by human, essentially an anthropogenically originated structure, or maybe change in any topography, how it has affected a habitat's configuration, we will be in a more better position to be able to delineate these differences only when we study before that infrastructure was built, how was the condition, how was the situation, and after, how it has been. Which means we will have to redo this particular task once before the infrastructure was present, and once yet again after the infrastructure, right? So I hope that helps. I hope I have understood what you were trying to tell us. I hope it helps. Thank you so much for sharing your views. We have Prem with us. Would you like to talk to us?
I guess Sanjay and Dipti, the expectation from this course, my expectations are lying to some extent to their expectations, because earlier I was working on wetland restoration project. So when I was working on wetland restoration thing, and when I have to design the intervention measures, it uh, it was more about a larger scale on a landscape scale. So I had to rely on someone else to give him or her my inputs, like what I wanted and what I don't want. So this takes a lot of effort to convince someone, and it is not possible that you will be getting the reliable output from the second person or the third person. So it's more about getting self-reliant, about doing our own stuff. And although I have stopped working on wetland restoration thing, I am expected to join some carnivora range expansion and home range project. So vegetation and habitat mapping is the main substrate for this kind of a studies. So I'm expecting to have a greater understanding of these things. Yeah, thank you.
Thank you so much for sharing that. I've recently become a wetland mitra. So I will share this link with you all, wherein you can learn a little bit about what exactly wetlands are, what are the ecological services that they provide. Recently, my brother told me about something called wetland mitra, because essentially I was studying the one of the Ramsar site along the west coast of India. If you might have heard of it, Vembanad Core Lake. And my brother told me, if you want to really learn a little more about these wetlands, you might want to prefer becoming a wetland mitra. So I happened to join that particular course, very exhaustive and very interesting course. I will share a link with you all. And to what Prem has shared with us, I'm very thankful for that. He really outrightly mentioned that he was facing difficulty in finding some secondary data, because it becomes very difficult for another researcher to trust on us and be able to give all the data that they have generated. Because it's much like the my data is my child, isn't it? I wouldn't want to give it to somebody else. Then in that case, how do we make our own data that is also reliable and that yields to our own research progress and our own output that is measurable as well. So thank you so much for sharing
Yes,
that answer.
exactly.
And
As you
I
talked
would
about the
also like to appreciate that you were ready to learn it. Thank you so much. Yes, Prem.
no, I was telling that I was working in Trinalveli district of Tamil Nadu. Like I worked there for last 10 and 11 months on wetland things. So we also had this wetland Mitra thing. We explored and we uploaded our data, like what things we have done to restore these wetlands and all. So I was just trying to mention this thing to you.
Yes. Okay. Thank you. Thank you so much for sharing. It was really nice talking to you all, and I'm really happy that mm, you all are ready to interact during the course as well. Let's make it a lot more um, interactive, a lot more sharing, a lot more sharing the other difficulties and finding answers to whatever difficulties that we face during this 1 month, and be able to complete our exercises during this particular time, right? uh, yes, so if anybody else would like to talk to us, anything else that they want to share, we are open for it. We have reached our time, that is 9. So if you would like to escape, you can escape from the meeting and have a great evening